Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering a new module, Applied Chemical Ideas, with a new particular inquiry question. Number 2, analyze analysis of organic substances. Conduct qualitative investigations for the presence in organic molecules of the following functional groups: carbon-carbon double bonds, hydroxyl groups, and carboxylic acids. Reference pages there. We're going to look at some methods that we could potentially use to differentiate or identify particular functional groups, and we're going to list them out. Now, just to recall all the different types of functional groups that we know of, that we've talked about in this Year 12 module or Year 12 course. We talked about alkenes, single bonds, alkanes, double bonds, alkyl, triple bonds, alcohols, our functional group there. We have the aldehyde group, we have the ketone group, we have the carboxylic acid group, we have the ester group, amine, amides. Okay, so there's quite a few that we've covered, and it is to your benefit that you understand what each functional group is and what they look like. Now, the test we're going to do is working out the particular functional group. Now, if you look at something like aspirin, this is the structural formula for aspirin. You can see that if we do know what the functional group is, we can obviously mass reproduce particular medications, pharmaceuticals, all those kind of things there. So the ones that we're going to investigate and what the syllabus has dictated is the alkenes, the carbon double bonds, the alcohols, and the carboxylic acids. Okay, so that's what we have here. All right, so the first test with the carbon-carbon double bond, what we can do is we can separate between alkanes and alkenes using bromine water. Okay, so bromine water is naturally a reddish-brown color. If it's mixed with an alkane, there is no reaction, okay, and there is no color change. If it reacts with alkenes, the bromine water will react with the alkane, breaking up the double bond, and in that breakage, the alkene will turn into dibromoalkane, or whatever alkane we get there, okay? So if you compare the pair, all right, we're injecting both with bromine water. You can see on the left here, progressively the color is turning more transparent here. So what we can tell is this is our alkene group. This was originally an alkane. Okay, so that's what we see there. Now, in terms of the science of how do we work that out, we know that if it is or what we actually know is both alkane and alkenes are colorless. However, for bromination to occur, it's an addition reaction. So alkanes are saturated hydrocarbons. Okay, so if it's a saturated hydrocarbon, that means it will not be able to form an addition reaction. Alkenes are unsaturated, so it has a double bond, so it means it can form an addition reaction. So we can contribute or attribute the decolorization of the bromine water with alkene because it's forming that colorless color that we're searching for there. You can sort of picture what's happening here is in the process, the carbon is broken up, latches on to one, okay, breaks the bond there, and then the other bromine attaches on to that as well. Okay, obviously you can use other sort of halogens to do the same thing, but bromine water is the safest one we have that we can use. The next test we're going to look at is how do we test for carboxylic acids. There are a couple methods. We can use Litmus blue. We can use sodium carbonate. We can even use the production of esters as a way of searching for the carboxylic acid as well. So let's go to the first one. If you compare the pair, obviously we don't have the carboxylic acid example, but it goes through the eye the same way. So ammonia is a known base. If it reacts with blue litmus water, it will stay blue. If it reacts with red litmus water, it turns blue there. If it's an acid, whenever an acid reacts with blue litmus paper, it will turn red. Okay, and the same thing will occur if it's carboxylic acid. So carboxylic acid will turn blue litmus paper red there. And that's how we can test out that we have the carboxylic acid there. Okay, the reason why it turns red is because the pigments in the blue litmus reacts with the hydrogen ions, and this chemical change changes how much or the type of wavelength that the bonds reflect. So instead of reflecting blue light, the bonds begin to reflect a longer wavelength of light. So longer wavelength is usually attributed to red light, and so that's why we see that color change turning into red. The next one we have is testing using sodium carbonate. So we know that when we react an acid with sodium carbonate, we'll produce a carbon dioxide because it's reacting with metal carbonate. Another way we can also add on to that investigation is if we funnel the production of that carbon dioxide into a tube of lime water, then we can see it turning cloudy, and that's another way we can find out that carbon dioxide has been produced, and therefore that sodium carbonate must have reacted with a carboxylic acid or some type of acid of that kind there. So that's an additional component in working out that we're getting a carboxylic acid there. Okay, so that's what we get there. Right, explanation. Oh, I have the same explanation here, so I am going to quickly change that up. And then you can copy it down as I go. So, and I do apologize I didn't fix this one up, but the idea is very simple. So we know that acids react with metal carbonates to form CO2. Okay, now if CO2 existed, so if CO2 existed when it reacts with lime water, so when it reacts with lime water, a precipitate is formed. Okay, so that's what we're dealing with here with this explanation of why we would want to use the carboxylic acid and sodium carbonate to work out if it's carboxylic acid we're dealing with here. So that's kind of the reasoning there. Okay. And as we know that acids do react with metal carbonates to form carbon dioxide there. So, that's adding on to each other. The next one we can do is to test for alcohols. So we know that with alcohols, there's primary, secondary, tertiary. So let's have a look at all the different ways we can do this investigation here. So the first method we can use is reacting sodium with the alcohol. Okay, after obviously we remove any excess water in the alcohol. So to remove any excess alcohol in water, we can add granules of a particular dehydrating agent, so say calcium chloride. Depending on the type of alcohol we have, the production of hydrogen gas will be greater or slower. So fastest for primary alcohols, slowest for tertiary alcohols. So this reaction, remember, if we react something with a particular alcohol, let's say, using the example of sodium plus, let's say, potassium hydroxide of some kind of alcohol there. Well, that's not alcohol. Ethanol. Okay, let's say we're using ethanol there. A byproduct of that production is hydrogen gas. Now we know that hydrogen gas is highly flammable, so we can actually use the pop test to see if we are using or dealing with an alcohol there. Okay, so confirmation that we do have H2 gas, then we can use the pop test there. The general equation we can work out is that, so we get an alcohol, we get our metal, and then we form what we call here an alkoxide anion. Okay, so that's what we have there, and this will be the thing that we use our pop test for. Another way we can test for alcohols is the production of esters. So if we use glacial acetic acid, so really concentrated acetic acid or vinegar, plus a little bit of sulfuric acid with ethanol, we can actually form an ester. So remember, an ester is something that has sort of a fruity smell to it. It comes from the formation of an alcohol and a carboxylic acid. So you can actually do the reverse. So the carboxylic acid one we talked about just then, if we react with an alcohol, we can also work out if we produced an ester and therefore work out if we have a carboxylic acid. What we do know though is for tertiary alcohols, they tend to have a lower concentration of ester produced, so it might be a little bit more difficult to detect that way. So that's just kind of explaining how we can use esters or producing an ester with alcohol to know that we have alcohol there from the acid. The final one that we can talk about is the test for alcohols using potassium permanganate. Okay, so what we know is by adding drops of acidified potassium permanganate, so having a little acidic concentration there, we see a disappearance of a pink color indicating the presence of a primary or secondary alcohol there. So as you can see, that's the color change we have. Potassium permanganate is sort of a dark purple color. If you add an alcohol into it, you'll see it changes the color, causing a change. Obviously, you can sort of use it as an indicator of some sorts there as well. All right, some questions for you to look at. What is the bromine test used for? What constitutes a positive test for bromine water? So how do we know what we found with the bromine water is what we were searching for? How would you carry out the test for a gaseous compound? What is one limitation of the test with bromine water? Okay, and then question 5, outline 3 chemical tests which may help identify alcohol. And question 6, one of these tests can be used in reverse to identify carboxylic acid. Explain this, what is it used for, and answers there as well. Okay, so that's pretty much what we need to cover in this lesson. It's a relatively short one because it's pretty self-explanatory. So have a look and see if you remember the difference of the functional groups. So what you need to recognize is all the different tests we can use to identify these 3 functional groups. These 3 being the carbon-carbon double bond, the alcohol, and the carboxylic acid. All right, thank you for joining in the lesson, and I will see you next time.